All right, let's talk about kinetic molecular theory. Kinetic molecular theory allows us to explain the behavior of gases using basic ideas from physics, okay, apply them to the movement of atoms and molecules. So these basic ideas are Newton's second law, which says that force equals mass times acceleration. Newton's third law, for every action there's an equal and opposite reaction. And we're also going to apply the idea of kinetic energy being equal to 1/2 times the mass times the square of the speed. So we're going to apply these to atoms and molecules, and we can see that we can use this to explain the ideal gas law. Okay? So, what are the assumptions that we make to explain ideal gas behavior? First of all, we assume that gas particles, okay, are point masses that are in continuous random motion. Now, point masses means that they occupy a negligible amount of space. So we're ignoring that they have finite volume. Okay, and this is an assumption that becomes valid the, when we're dealing with gases at very low pressure. More and more valid at lower pressures because then the volume of the container will be so much bigger compared to the actual volume of the gas molecules themselves. Okay, continuous random motion, evidence of that, okay, is known as the experimental basis for that assumption is the phenomenon known as Brownian motion. Brownian motion refers to movement of small particles that we can actually see through a microscope that appears to be random. And the explanation for why this motion is random is because these particles that we could see through a microscope are actually constantly being bombarded by molecules that we can't see. Okay, so there's a couple of videos that you might want to look on YouTube, look at on YouTube to explain Brownian motion. Let me see if I can pull those up for you. Right here, this video called Molecules in Motion. I put a link to this in the Moodle course site. Okay, and here's another one on Brownian motion that you can look at. Okay, so the basic idea there is these particles that we might be able to see through little tiny particles, which we might be able to see through a microscope. They're sort of random motion that we see from these particles can be explained in terms of collisions with particles that we can't see, and those are your molecules. All right. So there's no energy that transfer. We also assume that there's no energy transfer that occurs when gas particles collide with the walls or with each other. So we say in physics that the collisions are elastic. Although this is not really, strictly speaking, valid for individual collisions, but if we do average it out over all the gazillions of collisions that's happening within a sample of gas, then we can, the total energy transfer for all these collisions does average out to zero. So for simplicity, in applying the uh, physics to our collisions, we can make that assumption, okay, and arrive at an expression that will allow us to explain ideal gas behavior. We're also going to assume that the gas particles exert no force on each other. That's not true, but in the limit of situations where the ideal gas law is valid, okay, we're saying that the molecules in an ideal gas, particles, are so far apart that for practical purposes, we can, the assumption that they exert no force on each other should be valid. Okay, and we'll see in a later lesson when we talk about real gas behavior, then that we can actually make corrections for the fact that this is not strictly correct. But we're trying to explain ideal behavior here. All right. So how do we interpret the idea of pressure? Pressure of a gas is due to collisions of particles with the walls of the container. So if this is the wall of your container, your collision of a particle with a wall would impart a force on it. Okay? So okay, if you recall, acceleration is a change in velocity. So if a molecule collides, okay, let's just say it's colliding head-on with a wall, and then so it's going forward, and then once it collides, it moves back in the opposite direction. That's a change in speed, okay? Not change in speed, change in velocity, change in the direction, even though it doesn't change speed, because we're assuming that there is no energy transfer. So the kinetic energy, 1/2 mv squared, remains the same before and after the collision. Okay, but there is acceleration because it's changing velocity, it's changing direction. the fact that it's changed direction, that means that there's a force. The wall is exerting a force on the um, on the molecule or the atom that collided with the wall. Okay, so the wall exerts a force on the particle. The force is mass times the acceleration of the particle. Okay. The particle also exerts a wall on the force, according to the third law. If the wall is exerting a force on the particle to cause it to change direction, and that means the particle itself is also exerting a force on the wall. That's the third law, Newton's third law. Okay, so the pressure due to the particle, okay, is given by F over A. That's the force that the particle exerts on the wall divided by the area. So its pressure is defined as force per unit area. So if you have lots of these particles, gas particles in your sample, there's going to be a lot of collisions against the wall. And so if you add up all those forces, divide by the total area of the wall, you get the pressure on the wall.